All right, lesson 4.6. This is on volumes, and there's two ways we're going to think of this. One volume is when you have a known cross-section, and it's a square, a rectangle, a semicircle, an equilateral triangle. So that's here. And to understand volume with calculus, it's similar to understanding area, where it's top subtract bottom or right subtract left. But then you have to use the formula for this cross-section in the integration. So volume is an integration question. It's similar to area, where it's top subtract bottom or right subtract left. But then when we do that, we have to think through and we have to find the base of this. If it's, and we're going to learn later on about if you rotate it around, it creates a circle. We need to find the radius. Right now at the beginning here, we're going to use these formulas, and it's important to understand the base of each one that we're creating. So here we are. Volume, we're going to integrate using the area formula. And again, we're going to go top subtract bottom. If it's perpendicular to the x, if it's perpendicular to the y-axis, then all of this will be y, and then using the same formula. So in question number 1, find the volume of the solid whose base is this triangle. It's already been graphed for you, and whose cross sections are squares, perpendicular to the x-axis. So this is perpendicular to the x-axis. And what we have here, that's the base, and then the volume are these squares that are sticking out, coming at you. I don't know how to draw this, so that's the base and the square sticking up at you. And there's a bunch of squares, infinite number here, that then create that volume. So from 0 to 1, how would I find that if the base is a square creating this volume? And I know conceptually it's a little bit challenging at first. But let's just think about the setup. So the area formula is this. Think of S being the base. And this is where we're going to go top subtract bottom in terms of this. So what's on top is the line, and what's on the bottom is the axis, which is just 0, right? So when you subtract 0, we're just looking at the line. So negative 2x plus 2 is on top, subtract the bottom. So we're going to use negative 2. First we're going to integrate. We're going to go negative 2x plus 2, and we're going to plug that into the formula for a square, and that's what we're going to integrate. We're going to FOIL. If you FOIL properly, you would get 4x squared. Multiply these together and double it, and then 4. And then integrate. And then the last step, we're going to plug in 1, and then when you plug in 0, the answer is 0, so we don't need that. 8 divided by 2, just for fun. And then there's your answer. Ultimately, negative 4 plus 4, the answer is 4/3. Let's try it again. Here, we're going to set up, but we're not going to integrate. What happens if the cross sections are semicircles instead of squares? So now, think of the base. Now this is a semicircle instead of a square coming out at you. So again, we're integrating from 0 to 1. We need to know the formula for a semicircle. So that's up here, 1/2 pi r squared. And this is where it takes a little bit of thinking. So this base is actually the diameter, not the radius. So this is the diameter, top subtract bottom. So negative 2x plus 2 represents the diameter. The radius is half of that. So it's just negative x plus 1. That's what took some practice, and that's it. You're done. And then we could integrate it if I needed to. Number 3, set up but don't integrate an integral for the volume of a solid whose base is still bounded. Oh no, different one now. Negative x squared plus 2, y equals x. And the cross sections are rectangles perpendicular to the x-axis. Step number 1 is to graph this. So negative x squared plus 2 starts at 2, and it's a parabola that folds down. And then the line y equals x. And then what's bounded here, this is the area that's trapped between the two. And that's what we're going to look at. So step 1 is to find the bounds. To find the bounds, we make them equal to each other. Negative x squared plus 2 equal to x, and solve it. So I'm going to add x squared. I'm going to subtract. You still have positive x, and I'm going to subtract 2. I'm going to factor that, and then I'm going to solve it. So the two answers here are negative 2 and positive 1. And that makes sense in terms of when I look at my graph. So I'm going to integrate from negative 2 to positive 1. And then I look and think, okay, now what are we doing again? We're doing rectangles. Now rectangle is base times the height. And it says the height is 1/4. So I can put that in right away. Here the base is going to be top subtract bottom. So the top is negative x squared plus 2. Subtract the bottom, which is just x. And there's the setup. Turn the page. Setup. Volumes whose base is that circle. And whose cross sections are equilateral triangles but perpendicular to the y. So now we're going to go this direction if it's perpendicular to the y. So my first step here is actually to see what x equals, so everything can be in terms of y. So if it's perpendicular to the y, everything is going to be y's. So step number 1 is to subtract y squared. And then step number 2 is to square root. Now, I'm only going to take the positive square root that's on the right side. In fact, the positive one is the one on top for the y. And then I'm going to double that answer at the end. All right, so what are going to be our bounds from here to here is the radius is 1, so it goes from negative 1 to positive 1. So I like that. In fact, we're using our y, so it goes from negative 1 to positive 1. We're using our y values. And I'm going to go all the way across with equilateral triangles. So negative 1 to positive 1. I know this represents that length, but I want to double that length to go all the way across. So that length is only from here to here, so I need to double that. So the formula for equilateral triangle is root 3 over 4, and then whatever that base is, you square it. So it's this, but then I need to double that answer. And there's the setup. You know it's going to take practice. Same situation, perpendicular to the y-axis, but now we have rectangles whose heights are 3 times their bases. So we just said the base was 2, 1 minus y squared, right? That's the base. That's what we found. And then it says the heights are 3 times that. So you have the base, and then 3 times the base is the height. So this creates the base times the height, and then dy. Next. Circular cross-section. Sometimes you can revolve around an axis, and now the cross-section is a circle. So for a circle, the formula is pi r squared, And that base is now the actual radius, because as you rotate around, what you see is the radius, because it's going to rotate above it and below it. So let's set it up in terms of a circular cross-section. So set up an integral for the volume of a solid here that you're rotating around the x-axis, and it's from 0 to 1. So that's an integration question. It's a circle because we're revolving, so that's pi r squared perpendicular to the x-axis, and then this represents the radius, top subtract bottom. So that's just x squared subtract 0, and there's your answer. For example number 6, find the volume of a solid revolved around that bounded by this. So it's the parabola. X equals 0 is the y-axis. Y equals 4 and the y-axis. So this is right here. That's the area I'm revolving, and I'm going to revolve it around the y. So because of that, I need to see what x equals the square root of y. Instead, to flip it around, we're going to integrate the y value, 0 to 4. Because I'm revolving, it's pi r squared, and the radius, right subtract left, is just going to be the square root of y, subtract 0, or the square root of y. And it says actually find the volume. Okay, so then square root and square, just they undo each other, and it says y. Add 1 to the exponent and divide. Notice I can just leave pi in front. Plug in 4, subtract, plug in 0, and you have your answer. And that's 8 pi if you wanted to simplify it. Turn the page. Sometimes you have what's called a washer. A washer is like a donut. And for a washer, you have a big radius and you have a small radius, and you're going to subtract the two circles, and what's left over is the volume you need. So you have a big radius and a small radius, and this setup is understanding that you have a big circle, you have a small circle, and then you subtract it. So you have a big circle and a small circle. When you subtract that, you get the area and the volume that you need. That's what this is. This is just set up in an easier way to kind of plug in and use. So in example number 7, set up the integrals here by revolving the region by y equals, and it gives you the graph here, and do it about the x-axis. Now, it creates a washer when there's a space between the line that you're revolving around and the area that you're revolving. There's no space here. This is just a disk. So we go from 0 to 1. It's pi r squared, and then we plug in negative x squared plus x. That represents the radius. For the second one, there's a space. So we're going to have 2. So first of all, I just want to set it up. So it goes 0 to 1. We have a big radius, subtract a small radius, and have the setup to begin with. And the big radius, in this case, the big radius goes to the top all the way to the bottom. So top, subtract bottom. So that is the parabola, negative x squared plus x, subtract negative 1. So when you subtract a negative, it actually becomes adding 1. And then this is the small radius. So that's 0, subtract negative 1. That radius is just 1, and that's the setup. A little bit more challenging. Here, same idea. I'm going to do that up here. We're going to go 0 to 1. We have 2 radii that we're looking at, that we're revolving around. Notice the space here. That creates 2 circles. So the big radius goes all the way through the area to the bottom. That radius is 2. The smaller radius is, I'm going to write here, 2 subtract this, which is negative x squared plus x. And that's the radius that would go in there. And that's the setup. Number 8. Set up integrals for the volume. So here, we're going to revolve it about the x-axis. Notice there's a space here between this and the x-axis. So this is going to be a washer. So first of all, I'm just going to set it up, and then I fill in. So it goes from -1 to 2. The big radius goes all the way down to what I'm revolving around. So top, subtract bottom. So the top is the line, x plus 2, and the bottom is 0. So it's just x plus 2, take away 0. That's what it is. And then the small radius is this right here. It's the curve, subtract 0. So this parabola. So it's x squared, subtract 0, or just that. And that's the setup to find the volume. Last one here, part B. And then, of course, as we practice with the assignment, it'll get better. So, again, the setup. So now it's about the line y equals 4. There it is. And there's a space there. So it's going to be 2 circles. And again, it goes from -1 to 2. And again, I just like to set it up so I understand that and then fill in. So, and I draw it in. So the big radius goes all the way through to the bottom. So from the top to the bottom. So that's 4, subtract the parabola. And then the small radius is 4, subtract the line. And there's your setup. All right, Mr. G Math over and out. Till next time.